Okay, since recording's going, so yeah, sorry for the delay. A quick announcement before we start. Basically, one of the assignment questions you no longer like the one of the questions was incorrect. The denominator of the term do not cancel out. You just need to implement the code for now. Don't worry about deriving it. But the support code was actually correct. So today we're going to continue talking about trees in graphical models. There are different kinds of trees. All right. We're going to start with factor graphs, the third kind of graphs in graphical model that we mentioned over the last week or so. And then we're going to look at some lengths on the sum product algorithm. And we're going to briefly talk about extensions of the sum product algorithm and its other names. We're going to see more of this extension, let's say, in the Hida-Markov model section as well. So factor graphs, well, we have been looking at graphical models that represent joint probabilities of variables that are circles, such as x1, x2, and x3. And we have looked at two ways of representing this joint probability. If the nodes are connected as a directed cyclic graph, or base net, we write them in this following format. Basically, the joint probability is a product of each variable conditioned on its parent nodes. And if it is undirected, we write it in this other general form. Basically, we model the joint probability as a potential function over maximum clicks. So a more general form here is to simply model the joint probability function as a product of factors. And here, factors are drawn as square nodes, and factors are defined over subsets of nodes. In here, there's no specific constraint about which subset of nodes. For example, in this 3-node graph, we can have a factor about x1 and x2, another factor about the same 2 nodes, indeed. Why do we want, for example, this configuration of different factors about the same nodes? That's because for example, our input features might describe different properties. You imagine these are image pixels. The factors might be modeling, let's say, different spectral spectrum, like infrared versus visible light of the input of the pixels. And then we can essentially parameterize these factors somewhat flexibly. And then we have another factor that is about x2 and x3. We can also have a factor that is just about x3. And the joint probability distribution is simply the product of these factors. Right, so compared to an MRF, FA and FB here would have been in one potential function. In here, we can pull them out into different factors. So we can trivially see that the base net representation and also the MRF representation are special cases of these factor graphs. In MRF, the factors are constrained to be over maximum cliques. And you may ask, what about normalization? We kind of said normalization is a big deal, right? In here, and in this expression, there is no normalization. So we can say the normalizing factor Z is a factor 2. It is just over an empty set of variables, not over a particular variable, right? So that's the definition of factor graph. In other words, factors, the square nodes are connected to the variables that it captures. So, and you say, well, it's so flexible. What are the potential downsides and upsides, right? So, one directed or undirected graph can actually, in fact, correspond to multiple valid factor graphs, right? If we have fully connected x1, x3, x2, and x3, we can drop a factor that connects to all three nodes, or we can actually drop two factors, one describing the join of all three nodes, and another one describing the structure that's encoded in x2 and x3. So factor graphs are not unique, right? And if we represent this undirected graph using ARMA-Fs with the phi terms or the potential functions are unique, right? And the product of these two is equivalent to the potential function term. Similarly, if we have, let's say, this head-to-head pattern in Bayes nets, we can use the same factor graph as last page to represent this different joint distribution structure, or we can write up a different factor graph that has the joint term and also a term for x1 and a term for x2. This is useful when we would like to model, say, priors on x1 and x2. Right. Because the joint probability factors as basically p of x1, x2, and p of x3 conditioned on the two, we can say that we can make a factor that combines all of these, or we can make a factor for each of these terms. So what are some general properties of factor graphs? So we claim that factor graphs are bipartite. So a bipartite graph is a graph whose vertices are divided into two disjoint sets, U and V, such that every edge connects a vertex in U to a vertex in V. But no edge directly connects vertices within U or within V. So this is indeed the case for factor graphs because square nodes are only connected to circle nodes and vice versa. So we do one way to construct a factor graph is via the clique potentials, right? So create a variable node for each node in the original graph, just copy the circles, create factor nodes for each maximal clique x of x, and then set the factor to the clique potentials. As we already said, there might be several valid factor graphs corresponding to one undirected graph or a directed graph. So here's the example that we kind of mentioned but didn't go into detail, right? We kind of said that tree structures in directed and undirected graphs, graphical models are easy to do inference. There's another class of directed graphs that are called directed polytrees. They are not strictly trees. Like certain nodes can have multiple parents, but there's still no circles. They can be converted into factor graphs as trees, or in the form of trees. For example, if we moralize this directed polytree by connecting the co-parents, we get this undirected graph. And then we can basically have factors for each of the cliques. And then we can have factors for variables that have priors, right? So I'm going to state without proof that factor graphs for directed and undirected trees, as well as directed polytrees, they can retain a tree structure, right? And we're going to rely on this statement to derive this or basically talk to you about how to do some product algorithm for inference. That is to say, we can use factor graphs to actually, I would say, you may say, you can get rid of a circle, right? By just connecting the factor to all the nodes in the clique. So I can see Noel just asked the question whether it's worth forming a circle as well, right? The answer is sometimes. If we form circles using factor graphs, it's still a valid representation, right? So the joint probability is still the product of these three factors. The concern is that the encoding of conditional independence is kind of gone, and also efficient inference is also kind of gone, because like now we have loops, and if we use dynamic programming, we can't we can't do one or two paths through the graph and ensure that we have the right probabilities, as you will see. So yes, you can, and there are scenarios where you might want to do this, such as in Markov random fields with like pairwise potentials, right? Or for connecting neighbors for image segmentation. As you can see, it forms a grid. The image pixels form a grid, and no matter whether we create a factor for each edge or a factor for each, let's say, little square, it will still have cycles. But for that kind of Markov random field or for image segmentation problem, the solution is not message propagation or sum product algorithm anymore. There are better algorithms such as graph cut. So I guess this is to say that graphical model is such a rich class of models, and there are many solution strategies depending on the structure of the graph. Our clique size is small, our clique size is big. If we're, like, for example, people have invested lots of time to do graphical models for images, but if you have a social network, and there's some local structure, what is the right model? And also there's so for social networks, the traditional graphical model tools are not widely used, mainly due to computational reasons. But if after this session, we can start looking at some of the more recent algorithms, such as so-called graph neural network, from the message passing lens, right? So, and it will all kind of somewhat make sense. So let's get to it. So factor graphs allow us to describe the sum product algorithm for doing inference in general graphical models where its factor graph is a tree. So we're only dealing with trees for now. We're not going to be able to cover the general case, but if we can run this algorithm on factor graphs with loops, but it's not guaranteed to converge. Right, so our goal is to evaluate local marginals over nodes or subset of nodes. Remember last time we covered evaluating local marginals over chains, so right now we're just generalizing it. A variant of this goal is to find the most probable state, which is executed by the max-sum algorithm, which is pretty much the same algorithm, except we replace the sum with a max. So for, I guess, convenience, right? I would suggest a way to do a first understanding of this algorithm is to assume that all variables are discrete or even binary. And the marginalizations can be done as sums. In fact, for continuous variables, you can do the mental exercise. Basically, we replace all the sums with integrals, and then the conditional probabilities of the continuous variable conditioned on a discrete one will become, let's say, slices of continuous distributions. And the other way around, it's still sort of a discrete distribution conditioned on a particular value of the continuous variable. So these are covered in some detail in the linear dynamic systems section in later part of the corresponding book chapter. We are not going to have time to go through this. It's interesting though. So as a historical note, the sum product algorithm and factor graph were proposed around the turn of this century. Hi, Brendan Frey in University of Toronto, who is still doing active machine learning research. It's elegant algorithm. And 10 years before that, Judea Pro and others have proposed similar algorithm called belief propagation. It performs exact inference on directed acyclic graphs. So it's a special case of the sum product algorithm we're going to describe. As you can imagine, for Bayes nets, belief propagation, right? So we can, for Bayes nets, we can, let's say we have a tree, we can simply have a factor on each edge. And then if it's the Bayes net is DAG, then the resulting factor, it's still a tree, right? Or a polytree. Yeah. Okay. So here we go. We're actually going to describe the sum product algorithm top down. So the next 2 pages is the most notation heavy. Once we get through that, we're just going to basically look at the same scheme a few different ways, and that's all of this session. We're going to rely on mainly 2 facts. One is this sum product rule or distributive law of sum and products. So basically the sum of 2 products with a shared factor is equal to the product of this shared factor and the sum of things, right? So if we have, like if A is a sum of something, again, we can basically use this to unroll the expression. It's worth noting that, well, it's trivial to see that this is basically 2 operations, the sum and then the product. On the left-hand side, it's 3 operations. It's 2 products and then the sum, right? So there is a saving of using the expression on the right-hand side, or basically for summing, like moving the summation sign has advantages, right? So remember, we would like to evaluate marginals. So assume the joint probability we have is P of both X, as X is a vector. We would like to sum over all the other dimensions except this variable in question called little x, right? Remember our factor graph representation, this is equivalent to summing over all the other variables on this product of factors, right? And the product is over different factors. So this, the expression at the end here is basically resembling the left-hand side of the expression here. Basically, it's a giant sum over many variables, over like also a long set of, potentially a large set of product of factors, right? So we're going to repeatedly use this. Notice that we can also rearrange this factor graph probability definition into a form that's centered on the node X. What does that mean? It means that if we want to compute the marginal on the node X here, we're just going to say that, hey, we redefine, we essentially group the factor graph into according to neighbors of X, right? So any of X are neighboring factor nodes. So these are NE of X. They are this node, that node, and this particular node. Right, and we index them as F of sub S. Right. And so what is this big F then? So the big F is the product of all the factors in a group associated with this particular neighbor of X. So remember that factor graph is bipartite, therefore neighbors of X can only be factor nodes, right? And then also we rely on the fact that the factor graph is a tree. Therefore, so if we treat X as the root node, then these factors are its immediate children nodes, right? So this is the root, and this is essentially children nodes. And then this notion of X sub S is the set of all variables in the subtree connected to the variable node via the factor node f of X. So what this long statement means is that if the whole factor graph is a tree, then we can take X out, then we can essentially partition the rest of the graph as subtrees connected to the neighboring factors of X. So basically, this factor is connected to some other variable nodes, and there might be other factor nodes that are downstream, right? Something like that, and it goes on forever. But the important thing to note is that because it's a tree structure, all of these variable nodes that are descendants of this factor node does not overlap with the descendants of other factor nodes. Okay, so that's a mouthful, and this is where the top-down definition comes, because what we're trying to do overall is, as you can see in the rest of the page, so summing over almost all the variables except X is kind of hard. And we're in this first step, we're going to essentially partition this giant sum according to the factor nodes of X. And then we're just going to write the sum in terms of, hey, the rest of the nodes that are dangling off a particular factor node, right, or are descendants of a particular factor node. So that's the general direction, and we go there in two more equations, right? So this tree structure and the factor nodes leading the subtrees allows us to rearrange this generic factor graph expression according to these directly connected factor nodes, right? So we're just saying we arrange the terms, and all the factors dangling off f of X is grouped into this big f of S, right? Okay, we have done no work except replacing the product over all factors to the product over neighbors of X. And then for the products, like the other products, they're just folded into the big F, right? Because as you can see, it's the product of all the factors in the group associated with the factor. Excuse me, 1 second. Okay. Okay, we do this. And in the next step, what happens is that we exchange the order of product and sums. This is due to 8.53. So we have a sum over a big product of factors. We rearrange this term, and then we essentially we pull the product to the front, which saves some computation according to this. And then we essentially also regroup the rest of the nodes that needs to be marginalized over as the set of basically according to x sub s. These are the set of all the variables in the subtree connected to the variable node via the factor nodes, right? So basically it's a gesture to say x of s is all the nodes that lives in this light blue cloud. So we just wrote that, and that's valid, okay? It's just a number of new notations. And now what happens is that we define this inner sum as a so-called message. So message passing or sum product. The messages are not really like messages in the text message sense. It specifies an order of computation over the graph. And it's basically sums and products of the subset of the terms that we're trying to compute. So what the rest of this page does is essentially say, yes, we did. The only work we did was to rearrange the terms and exchange product and sum. And now we just going to define this term inside this giant sum over the subtree of the rest of the nodes as a new term called mu of from f of x s to x, basically the message from a factor node to a variable node, right? It's defined as the product of all factors, including itself here, actually, that are with the remaining nodes marginalized out. Okay, this is the first step of sum product algorithm. Let's look at an example, a simple example here. So if we have a factor graph, so here is the last two expressions repeated. We're going to use them here, right? So if we have a simple product factor graph like this, so we can see that the joint distribution P of x is just these three terms. It's a product of FA, FB, and FC, right? Each connected to two variable nodes. We would like to marginalize out x1, x2, and x3, leaving x2, which is the marginal we wanted to compute. What we do is we essentially exchange the order of product and sums, right? We take f of a, for example. We take the product, or basically the product here, because there's only one factor, the product is itself, f of a, marginalized over all the nodes that sort of connects to x2 via f of a, which is x1, right? So this is essentially the f of a, right? Little x, which is x2 here, and then x of a. In here, x of a is only one node, x1. So this is what this expression means. And according to A.63, the marginal probability is 3 of these sums, because x2, the node x2 has 3 neighboring factor nodes. Okay, so we saw the first step of sum product algorithm and implemented it. Yeah, for a simple product, simple graph, right? We're going to encounter this simple graph again in a little bit, but I hope this is informative. Let me know if there's a question. If not, so let's look at this f of s, capital F of x, as sort of a more, in a little bit more detail, right? You say, right, we've defined what's called a message propagating from a product node, from a factor node to a variable node. by symmetry, we will ask, what is the message from a variable node to a factor node, right? So if we look into this big F of S, it's said, well, it's a product of all the factors in that subtree. So we first pull out the root factor, which is little f sub s. Assume it's connected to m variables, x itself, and also x1 through x big M. Note that while the tree decomposition terminology is recursive, basically all the nodes connected to this factor node is a subtree, and also all the other nodes that are connected to f of s through any particular one of these x1 through xm's, they're also a subtree, right? So what this expression does is that, oh, we take this big f of s, now I'm just going to then partition it into the factor term and then the remaining factor term that are connected through x, the small m, right? There's big M number of them, and I'm just going to call these terms G. So this capital F and capital G business, they are notations that are only required for sort of mentally deriving the sum product algorithm. But when we implement them, we only need to work with these mu terms, which we keep track. Right? So here we go. So we have decomposed the capital F. Now we just need a little more notation since we have notations for the neighbors of X. Now we need notations for the neighboring nodes of f of s, which is essentially X itself and then all the other nodes 1 through M. All right. And we can also have neighbors except X. So here we go. We start from the factors we already defined, basically the message from f of s to x is essentially, remember we were summing over the capital X of sub s, which is x union these, let's say, children of fs. We know that we wanted to keep lowercase x, so we're only summing through x1 through xm. We plug in the equation above. The first term is a factor, and then a product of these g terms, right? And notice that the sum here only involves the direct descendant of f of s. All the rest needs to be marginalized out as well. So therefore, the sum is inside here and directly in front of the relevant g terms, which are also sort of non-overlapping because it's a tree. So again, we did all the work for this slide in this one line in terms of exchanging sums and products. The next step, again, is by just defining a new notation. You say, oh, this summing over the g terms by marginalizing out the children nodes is nice. We're just going to call them basically the message from x sub m to f of x. So basically that this defines this expression 8.67, marginalizing all the product terms over all the nodes connected through this particular node, including that node is actually not including that node itself, is defined as the message that goes from a node to a factor. Okay, to revisit, you may say that, well, right, so you have just done this in a recursive fashion, right? So there's mu messages from factors to nodes, and then the messages from nodes to factors. Where is the real work done, right? You will say. So here it is. The real work is in, let's say, deriving the factor to the node message from the previous messages, meaning from the node to factor message, right? So the real work, the computation is done in here, right? So we're multiplying the previous messages, a product of we're multiplying the messages from these nodes that goes into this factor. We first multiply them together using this operation, and then we multiply the whole thing with the factor term itself. And then finally, we marginalize out these directly connected nodes. So in fact, the work is done here in 3 steps, right? Multiply this, multiply that, and then get rid of or marginalize out the nodes. So that's pretty much it. So let's do a recap. Right, so we have 2 different kinds of messages, from factors to nodes, and then from nodes to factors. We kind of went through how we derive this one, the factor to node message from this one. We can try and see this the other way around. So this is still the same expression we were looking at. So imagine we have, let's say, factor to node messages coming in here, and now we want to derive this. So in this case, it's actually simple, because what we are doing is that we're simply doing a multiplication. Because this is a variable node, or the factor node, we're just going to do a multiplication of the factors. As in this. So we're just going to do a multiplication of the factors that are connected, or factor to node messages that are connected to the corresponding node. So we're going to multiply the messages from here, and here. And yeah, as necessary, we'll marginalize out that particular variable as well. So, so that's it. Right, so this is what it's saying here. In order to compute a factor to variable message, we take the product of incoming messages along all the other links into the factor node, multiply by the factor itself, and marginalize over all the variables associated with the incoming messages. The factor node can send the message. So this is the order of computation business, right? So this factor to variable message can only be sent after it has received all of the incoming messages. So basically, we have to compute the product of factors essentially from a bottom-up fashion if we're looking at an upside-down tree, right? So leaf to root is the order of computation, or order of passing messages. Okay, so this is another general statement that's taken from the Frey's original paper. What it basically says is that the marginals on a particular node is the product of the messages from its factors, from its neighboring factors. So node V, there are several edges connected to it. Let's say E1, E2, and E3. And then their neighbors are factor nodes, right? Like this. So node marginal So in here, in the previous few slides, we were essentially implicitly assuming that we are centering on a node that we want to marginalize over. And in a few slides, as we can see, this is more general. Basically, we can compute all the messages and then wait until they're all done. And then for each node, we collect these messages by multiplying them to compute its marginal. So basically, no marginals are product of the incoming factors. And a message sent from a node V on an edge E is a product of the local function of V. Basically, if V is a factor node, multiply the factor itself. If V is a variable node, it's just 1. Then it's just a product of the messages. With all the messages received at V on edges other than E. Right? So there's an implicit direction, and then summarized for the variable associated with E, where summarized here means like summed over, marginalized over. So this is a shorter but more compact, but like expression of the sum product algorithm in general. Once you have sort of made sense of it once, you can try and remember the more compact form, right? Maybe that's so. As you can see, this definition did not need the capital F and G's, but I do think the F and G's helps us understand what's going on in the, say, when we propagate, like move conceptually from the root to the leaf in a subtree, whereas the actual computation is from the leaf to the root. Of course, if you have done your computer science degree or have taken like the intro to CS, this kind of computation structure is quite prominent, right? It's quite like common in recursion structures, right? So, okay, so how do we start, right? We talked about the recursion step and the work we're doing in the recursion steps. So how do we start? So we see, if we're doing the marginal of one node X, then we can consider it as a root, because in an undirected tree, it doesn't really matter which node is a root. We can just pick any one. And then we start at the leaf nodes. If a leaf node is a variable node, then the first messages is sent is simply 1. Again, these messages are going to get multiplied. No new information is 1 in terms of multiplication, right? And if the leaf node is a factor node, then the messages is sent is the factor, right? So when will leaf nodes being factor nodes? That's when, for example, a few pages ago, we were modeling the prior of parent nodes in the base net, right? So these initializations you can derive from the general formula, and it's shown to be correct, right? So, and you can see that, hey, what about normalization again if the factors are unnormalized? The answer is actually easy if we're computing marginals, because as we say, so the unnormalized marginal on the node X is simply a product of all the factors Fs connected to X, right? On S. And this is essentially a probability vector, right? So we know what the value of these messages are. So it's product of the neighbors. Then we just need to renormalize this probability vector, right? If we're computing marginal for binary variable, we're going to get two sets of multiplications. One set for the terms where X is 0, and another set for the terms where X is 1, and then we renormalize. Then we're good. And normalizing in one dimension, well, again, thinking discrete variables, is never quite a big problem, right? Even if we have huge state spaces, for example, language some recent model or versions of language models will have like 500,000 words. Normalizing that is not a big deal. It's when we have high dimensional space of these x's, then normalizing become harder. Okay, let's look at our simple toy factor graph again. And now, right, so we can say that we decompose it in this unnormalized form. Then how do we do message propagation on it, right? And here we're also being ambitious, meaning that we would like to compute all messages so that we can compute the marginals of all nodes in one go, rather than saying I'm going to treat the node I wish to marginalize, compute the marginal on as the root, and then do one round of message propagation, right? The basic claim here is messages can be shared. Here's how we do it. So right now we arbitrarily choose, before we were working on x2, right now we just choose x3 as the root. And our first pass basically do so by starting from the leaves, right? So from the leaf node x1 and x4, we have two messages that are 1. And then we propagate this to, so there are 3 terms. This is FA. And then x4 is connected to FC. And then x2 is connected to FB, right? So the next set of messages that are being computed is basically from FA to x2, right? There's only one term here, FA itself, and it's marginalizing over x1, right? So this is the x1 gets summed up or marginalized out first. Similarly for x4, same expression here. And now that we have computed these two messages, so the messages from x2 towards the direction of x3 is ready to be computed, right? So the outgoing message from x2 is hence the product of incoming messages, simple product of these two things, because it's a variable node. It does no work. It's only the factor node that does like quite a lot of work, right? The only work it's done here is multiplying them. So since we already have these two expressions, we multiply them together. Now, yes, there is one remaining factor node. So what we do is we multiply the incoming message x2 to FB with the factor FB itself, and then marginalize out the node that's sort of downstream in the leaf direction, right, with sum over x2. So this is what FB sends to x3. All right. So you may say that, okay, this is actually one complete pass, right? After this, we can compute the marginal on x3. But what about, right, from root to leaf? Right. So turns out that if we choose x3 as the arbitrary root node, we can essentially initiate messages from x3, or basically flip the order of the tree entirely, and then compute all the messages in the reverse direction using the same method, right? If we start from x3, the message E sends is 1, and then the message that f of B sends is simply itself marginalize x3 out, and we can essentially do the same thing until we reach the leaves. What's the advantage of doing this? Is that once we have these two sets of messages, computing the marginal of any node is a simple, essentially pick and choose exercise, right? So if we now want to compute the marginals on x2, we can simply say that the margin of x2 is the product of all the incoming messages, and we just pick them out, right? For example, what did we do here? So which messages are incoming, right? So this is fc to x2. This one is, this arrow is fa to x2. It's from the same graph. And then notice that the fb to x2 message is on along the other graph, right? So we just pick out these three terms according to the above. Write out their expression according to what we just did, and verify that this is actually correct. If we stare at this and we say that now we pull all the summation signs to the front, we don't actually compute it this way. We compute it using, this is the computation. It's done here. It's the more efficient. As we can verify, there's, if x, let's say all of the x's are binary, we're looking at 3 multiplications plus 3 additions, right? Whereas if we're doing this one, we will be doing actually 2 multiplications, my bad. We'll be doing basically a times 2 multiplications. So this is where we save computation. As you can see, with the number of nodes growing, the saving in computation is exponential. Basically, if we're doing this brute force, it's actually, if each node has up to k values and there's d dimensions in x, then this is exponential, but not for the one expression above. Okay. So here's basically another summary to look at the sum product algorithm, because it's so cool, but it's also a bit abstract, right? So the general idea here is we interchange summation and products. We push sums as far into the product as possible, like what we saw, right? So we push sums. So if we're only summing over a small number of terms, that has more overall savings rather than summing over a large number of products, right? And we view partial sums messages, and then they're coupled by factors. We're propagating messages along the direction, the order of computing these partial sums and products, essentially. The messages are simply functions of some variables, right? So this is essentially a terminology thing. I think it's convenient to think about the order of computation as message passing. So we exploit the tree structure of the factor graph to divide a long giant sum into partial sums, right? So the tree structure is crucial. As we saw, if we have a tree structure, we can do compute all the messages in 2 passes over the tree. If there are loops, basically it doesn't stop. In other words, if there were a loop, let's say here, then I can actually compute a different version of, say, the message from this factor node to x1 again, through what I received from here, right? So if there are loops, I won't have one unique version of the message. Depending on how many passes have gone through the loop, the message will change, and that's bad, right? So generally you won't converge. So people still do loopy graph propagation for a few steps to help inference, but it's generally won't converge. So this approach that we just talked about is known as belief propagation in special cases. It's also known as message passing. We've been talking about messages for the past hour, and it's generally called sum product algorithm. Okay. So this is also to reiterate, we pretty much already said, if we would like to compute marginals for all variable nodes in a graph, the brute force will be run the entire algorithm with each node as the root. The more efficient version is to arbitrarily choose one root in the graph and then propagate messages from leaf to root, propagate all messages from root to leaf, and then just take a product of local messages that will give us the marginals. It only doubles number of computations rather than doing it like d times, right? So here's a quick note about generalizing sum product, right? So there is, right, in year 2000, there's this really cool paper called the generalized distributive law. As we said, the sum product algorithm it's yet another instance of this large class of algorithms called dynamic programming. It's used in so many different places. It's a divide and conquer strategy. Roughly every other class in computer science you encounter this, and then other class in the rest of engineering, such as electrical engineering, like if we talk about decoding, operations research, when we talk about the knapsack problem and so on, we'll encounter the same thing. So the generative distributed law basically says it's not restricted. What we did is not restricted to sums and products, right? The abstract theory is that a set, if there's a set, for those of you taken algebra, you might be familiar with two associative operations satisfy the distributive property. It's called a semi-ring. So in plain English, the goal of this generative distributed law, it says one can replace sum and product in a previous algorithm with other operations. One concrete thing that this allows us to do is decoding or find the maximum, most likely configuration of node values, right? So basically, if we replace plus by a max, right? So plus in probability terms is, say, averaging or taking expectation or marginalizing. If we replace plus by a max, it still holds, right? And like multiplying by summing, right? So as we can see, maximum of the product A, B, and C is equal to essentially A times the maximum of B and C, because A is a constant, we can pull it out, right? So this leads to what's called a max product algorithm that allows us to compute, let's say, argmax of X over a joint distribution P of X. So you may say, hey, this is computing the argmax is essentially the Markov random field for image segmentation problem, right? So over the probability of each pixel, we want you to compute argmax over all the pixels, which state it is, whether it's foreground, background. It is right, but the only caveat is that the MRI for image segmentation is loopy, so we can't really plug in sum product or max product there right away. As we will see over the next two sessions, so we are going to essentially specialize the sum product algorithm into hidden Markov models again. There's a new set of names there. It's called forward-backward propagation, which is pretty much the sum and product algorithm. And then the max product version in HMMs is called the Viterbi decoding algorithm. It's very useful in, say, speech recognition and also sending, basically communications, decoding what's being sent given a noisy operation. There are two related terms to sum product The first one is called the junction tree algorithm. I remember when I learned BaseNet in the early 2000s, this was taught as the preferred algorithm you will use. I think, yeah, some product was just invented then. It wasn't as well known, right? So the junction tree algorithm is a correct algorithm for performing exact inference in general undirected graphs. So for directed graphs, just moralize it, right? So what it does is essentially cast in factor graph terms is that convert undirected graph, directed graph to undirected graph, and then create a factor for each click or in the graph, right? So the complexity naturally is the grows exponentially with the basically the size of the largest click. So the computational complexity for the sum product algorithm is actually dominated by, like, we basically were saying that long sums are bad, right? And the long sums are essentially the size of the largest like undirected click again. So basically what we were saying before, where did we have this long sum, right? These two slides where we say, oh, everything in here is a product, and then we're doing the sum over all the n variables, right? So this is the complex part in the sum product algorithm. If we have basically factors that are connected to lots of nodes, then these will become the computational bottleneck. So that it's essentially the same, oh, sorry for the wrong set of nodes, as the junction tree algorithm. Basically, computational cost is determined by the number of largest clicks. In the factor graph, the click size is reflected in the connectivity, how many edges that goes out of a factor, right? So we talked about factor graphs with loops, right? So loopy belief propagation is essentially referred to the operation of doing some product algorithm on graphs that are not tree structures. The graphs have cycles, and then therefore the information flows several times through the graph. So we initialize by assuming each unit, the unit message has been sent over each link in each direction. So in here, because the messages keep changing again, we're not restricting, like, just for simplicity. It doesn't make much difference. Basically, it just amounts to us taking one more pass, right? We just initialize with unit messages on all edges, no matter whether it's a leaf node, whether it's from a factor node to a factor node, doesn't matter. Just initializing them with all ones, and then multiply, like do the same thing, multiplied by the factor and modularizing over. The convergence is no longer guaranteed, and there is not much we can say about this, aside by saying, yes, you can do this. It might do something useful in certain cases, but you don't get any like nice guarantees like in trees. So that's pretty much all. We spent a fair amount of time talking about factor graphs. We looked at and talked about the sum product algorithm pretty much inside out 3 different times. And then we have mentioned the extension of sum product algorithm into max sum algorithm or bit-to-bit decoding, and also junction tree algorithm, loopy belief propagation, and so on. So now you know a number of like new names that refers to graphical model inference techniques. Is there any questions for today? Let me just find the button to stop the recording.